Okay, assertions as applied to design verifications. In the previous lectures, you have seen how to write a design in Verilog, and in just this lecture given by the Kamalesh, he told that how we can write test bench so that we can drive the inputs to the Verilog in Verilog structural code and can get the outputs to verify a design is correct. So in this lecture, I am going to figure out these things that we will introduce just briefly what does an assertion means and why it is used actually. And assertion-based verification, how we can verify a design by using those assertions. And then typically we will use system Verilog language to write how we can write this assertion using system Verilog language. And there will be an interactive sessions where we will discuss about there will be an interactive session where we will discuss about little bit of tidbits about the assertions, and we will conclude. So let us briefly go into the introduction. Why design verification? Actually, there first we get some requirements from the customer that we need to build a design. These requirements are specified by the customer with the help of the requirement engineer, and the design team from these requirements builds the design or implements the design, which is a structural code. And on the other hand, the verification engineers from these requirements write specifications. It is often the case that the implemented design does not match with the specification, as you can see here. So we need design verification, and typically nowadays almost 60 to 70% of the time is wasted on, I will not say it is used in design verification. So then why properties or assertions comes into picture? So to verify a design, you can see that we need to have some important behavior, some specifications that the design should obey. These are specified in the requirements, from where we actually see those. We actually specify the behaviors in terms of those requirements, and the design team independently implement those design, and we try to find whether there are any errors or not. So these interesting scenarios, we capture them and through by assertions. If you remember that you have written a C code like this. In this C code, it takes two integer values x and y and just divides them and prints the integer value of x by y and outputs it as z. And I think you have all familiar with the assert statement there. Yes, you have used those. So one of the interesting scenario is that if y is 0, what will happen? So if y is 0, then this assert y not equal to 0 will just give an error message and will terminate from there. But if you allow this code to run, then it will division by 0 error, an exception will occur, and the code, it's an error in the code, which we don't want here to be. So this is an assertion. But the difference is that which you have used in this assertion, that you specify a boolean expression here, y not equal to 0, or a and b not equal to 0, like this. But in design, as design is simulated over the time cycle, so you need to have those time steps like in your assertions to capture. Actually, if you see this, if request 1 and request 2 are on, then in the next cycle grant 1 will be on, but grant 2 will not be on. So it is not actually a boolean formula. It spans over time. Request 1 and request 2 are on in this cycle, and in the next cycle grant 1 will be on, grant 2 will not be on. So in each time span it's boolean, but over through the time span it's a sequence. So in these things of specification we capture by assertions. These are interesting scenarios that we want to verify. So when we simulate the test bench, we just put these behaviors into our hand and check these behaviors are matching when the design simulates or not. So what is an assertion? An assertion is a precise temporal description of some specific behavior of a design. By the temporal, I mean that the behavior is specified over this time span. It's not. It may be an individual. It may be a behavior specified in individual clock, but essentially it must spend over a time period. So its sole purpose is that what designer thinks to be implemented and what he has implemented. Yes, there is a gap between these two. Essentially, in large designs, there is possible there is a gap. So assertion describe the expected and unexpected both kind of behavior. By unexpected behavior, I want to mean that safety, like you have seen the mutual exclusion. It's an unexpected behavior that two of the requests will automatically be granted simultaneously. So mutual exclusion is an unexpected. This expected and unexpected both kind of conditions to verify. So in brief, assertions captures those functionalities of the design that we need to verify. Like this. After request, acknowledgements must come 1 to 3 cycles later. What does it say? That it spans over time. That first in the clock cycle 1 request comes here, request is 1, And acknowledgement must come within the next 3 cycles. It may come in 2 or 3 or 4. So it's an assertion. You capture some specification or some behavior that the design need to actually behave like this. So this is a certain type of assertion. And the popular frameworks for this assertion specification is that people are using OVL, Open Verification Library, Sugar from IBM, Property Specification Languages, PSL from Accelera, ForceSpec from Intel, OV OpenVer assertions from Synopsys, System Verilog assertions from Accelera. But System Verilog assertions are more familiar one and a recent trend nowadays, and we will go through it in the next few slides. So how to write in assertion? Earlier days, the high-level description language people used to build the design, they used to write assertions in them. But it's very complicated to express those temporal properties throughout the design. I mean, it's unreadable. If you specify one, then in the next clock cycle, this in the next. If it spans over 40 clock cycles, it's inefficient, unreadable, and reusing is also difficult. But recent trends where you use PSL, SV, or OVA, this specialized assertion specification language gives us a chance to reuse it to build it more sophisticatedly, and it actually helps in design verification very much. So we will see that System Verilog is a recent trend. It's a hardware verification and description language, and a choice for the design and verification engineers. And what it essentially helps us is that we can design using System Verilog, we can verify using System Verilog. So everything is done under one roof. Actually, the System Verilog provides that support. Now, actually, the brief idea about assertion is that it is a behavior. Then what do we need such behaviors to verify, and how will it help in verifying? So we come to assertion-based verification to discuss it. Actually, you know to write a design in HDL in Verilog code. You have written in previous week, I think, and he has mentioned that test bench also can be developed using System Verilog or Vera. We will see in the lab how to develop a test bench. Now, if we simulate, actually, test bench simulate the design by driving inputs and taking the responses. And in assertion specification language, like in OVA, SVA, we specify assertions formally. And in the simulation framework, when we bind those assertions, when the test bench gives input, take the responses from the output, we find that often sometimes in the case some assertions get satisfied, some assertions get violated, and the assertions that gets violated is the behavior that we can't capture. Actually, this is the errors in the design. More detailed, the actual cycle, the actual simulation-based validation cycle looks like this. First, there is a specification. It may be a timing diagram which is specified from the requirements. The design team separately builds a DUT, which is device, a design and the test. And from this, we build a test plan which specifies the behavior one by one, that we want to drive this, capture this, and verify these functionalities. This kind of a rough test plan is provided, and from there we write test bench and correctness properties as assertions. We simulate them over the DUT, the test bench, and assertion monitors which assertion. It just ticks. This assertion 1 gets validated. Yes, no, this ticks it. And there is a coverage monitor. The coverage is an important term in verification. Actually, our goal is to cover as much as the behavior which is specified to the test plan, and so that we can check that these behaviors are specified, these are not. So these behaviors have to be implemented. So this coverage monitor, this coverage term means is that you have 40 properties or specifications, and you have verified 30. So 30 by 40, 3 by 4 your coverage. This coverage monitor actually monitors this coverage issues. So assertion-based verification, the design intent is expressed using assertion. The intent, the designer what he wants to express, and simulation, as he mentioned in the previous lecture, is done as usual. Here is a test bench. Here is a module under test. This test bench provides inputs to the module under test and gets responses. In the interface, we provide an assertion monitor there. We just looks to the assertions and checks that whether it is true or false or not. So assertions finds more works faster because it captures the functionality of the design and which the designer want to be in the design. Assertions isolate the source of the problem. And assertion-based verification can be adopted incrementally in the sense that it fits with the existing RTL flow. As we said that using System Verilog, we can specify the design, the test bench, the assertions together, and designers are already familiar with safety properties like the mutual exclusion property. These are the safety properties. And assertions on interface becomes constants for formal property verification. This formal property verification will follow. Actually, the assertion for the verified assertions, we use them as assumption in our in the formal property, as he have said, is that like theorem proving. You have an algebraic expression, you just deduct to another algebraic expression and see that whether they are equivalent or not. This is what the formal property verification will look like. But these assertions or these properties will help us to get some assumptions so that our proof become easier. As formal property verification exhaustively tries to find all the behavior, behavior that we want to verify, it is often the case that it runs out of capacity issue. So this will help us to actually have them within the capacity. And the design team will continue with their existing simulation flows, and to plug the verification hole, we need those assertion and assertion based verification. So where this methodology fits, if you have a single module, you can verify it using formal property verification, because its behavior are small, the exhaustiveness is limited, so that it can fit within the capacity. We can exhaustively verify this behavior. When the module becomes integrated in a block, then sometimes it may not be possible. So dynamic analysis, that is simulation, is needed. You cannot capture all the behaviors exhaustively, and in an integrated design, as you can see, it's never possible. So simulation is predominant, and to plug the verification, plug those gaps, the bugs, we need assertions. So actually assertions fits there. Now, how we can write this assertion? This is the main topic what I want to discuss in this lecture, how to write these assertions. So there are sequences, properties, and clock domain. We will discuss one by one. Sequences. As you have seen that these behaviors are spanned over time. So it's a sequential behavior. In this time cycle, such thing happens. In the next time cycle, such thing happens. Defined as a list of system value of Boolean expression in a linear order of increasing time. In each type span, a Boolean expression happens. Either request 1 is on or request 2. In the next time, some Boolean expression. So it's a combination of Boolean expression which spans over time. And a match of a sequence occurs when all the expression becomes true in a clock cycle. Actually, the evaluation attempt starts from a cycle where the first Boolean expression matches, and then in the next cycle this matches. On the total Boolean, temporal or sequential expression matches, we said that this is a total match. Let us take this example. Sequence S1 at the rate of passage clock, A #1 B #1 C end sequence. This is a sequence. At the rate of passage clock means we want to validate this sequence in every positive edge of the clock. #1 specified the delay. So the evaluation attempt will start when A is 1. Look at this timing diagram below. The evaluation attempt starts at cycle 3, where A is 1. This is the first clock tick where A is 1. It will try to find whether in the next cycle B is 1 or not. How do you find the simulator in the test bench? It provides inputs and validates those responses, and assertions are inside. It actually checks whether B is 1 in the next cycle or not. If in the next cycle B is 1, it's fine. Okay, let's proceed. In the next cycle C is 1, we find a match. So this sequence matches the cycle 5. It may be possible that in the next cycle again the sequence matches. At the end of passage clock, we validate this sequence. When first Boolean expression matches, we start evaluation. When it ends, we get a match or we don't get a match. So in this way, we proceed. Actually, sequence can also be with arguments. It may be with like this data en, CBE equal to en and #1 data. Look at that. Each expression is a Boolean expression which spans over this time, and it's less like a function in C. It can take also arguments. Actual argument can replace this identifier expression, everything. Look at a realistic example like cache access logic checker. The specification that we want to verify or want to monitor is that cache access logic should assert the cache access logic done signal for only one cycle. So what we have to do at the passage of clock, cal done, not #1, not cal done. That means it will only be asserted for one clock second. The next clock cycle it drops. When this happens, this sequence gets true. Now the important question is how will specify. Okay. This sequence request order at the rate of passage clock, #1, not cal done. So the important question is how we can handle the repetitions. So if I want to say that A happens, then the next 4 clock cycle B happens, and subsequently in the next cycle C will happen forever until the end of simulation. How this kind of situations can be specified? So we must have to. There must be some way to specify the range of it. There are 3 types of repetitions: consecutive, go-to, and non-consecutive. The notations are like consecutive is by this star, non-consecutive is by this arrow, and go-to is by this arrow, and non-consecutive by equal to. We can also specify range. Here it means that if we only specify one integer like x here, it means that for the next x cycles this thing should happen repeated. And by this x colon y, I mean that from like 2 colon comma 10, that means for next 2 to 10 times this thing should happen. We will illustrate it more details in the next slides. Like that, consecutive repetitions are sequences is consecutively repeated with 1 clock cycle delay between repetitions. Look at the top sequence. What does it say? That A in the next clock cycle B will 3 times B will be 1, and then C will be 1, then we will get a match. So if we elaborate this, this becomes this. As B is 3, it is easy to write by this also, but when B will be 40 or 50, it's a tough job for the. So the consecutive repetitions, the timing diagram will be like this. When A is 1 in the clock tick, the evaluation attempt starts. That is here in the 3 clock tick, third clock tick. Then we will try to see whether the B matches for the next consecutive 3 cycles or not. This 4 it matches, yes it is 1, 5 it is 1, 6 it is 1. And in the next cycle it C matches, yes it matches. So we get a match. And in the real case, like say that a master should not reassert its request signal until the current transfer terminates, like this case. Suppose it will reassert only when either cal retry or cal done is 1. So not request is there, and if both cal retry and cal done are not asserted, then it may be till the end of the cycle. Then it will never come its requests up actually. This dollar symbolizes the end of simulation until we simulate it actually. But if it finds any cal retry or cal done signal once, that means that actually the current transfer will terminates. So till then it will not assert its request, but in the next cycle it can. So this timing diagram, the evaluation attempt starts from here, this not request here, and we can find here also that cal retry and cal done is also low. And in these 2 cycles are there low, and then in the next cycle we find that cal done is 1 when the request is low. So this sequence matches here. This isn't practical. Yeah. Dollar is the end of simulation. That means what we want to say in the previous example, what you have seen that B will repeat 3 times. But if you have to specify that B will repeat from 3 to end of cycle, it can repeat 3, 4, 5, 6 till the end of cycle. So how can you specify that? You specify like this. It cannot repeat any time also, but it can repeat till when the simulation is continuing. Now the go-to repetition. The difference is that in go-to repetition, B will happen for 3 cycles, but there may be delay in between. That means first A started a match, then we can have a B, we cannot have a B, we can another thing. But when 3 times B matches, the last time when B matches there, the next cycle will obviously be C, otherwise it is not a match. Like look at the simplified version, look at not B here for it can be there, cannot be there. This thing repeats for 3 times. I mean a Boolean expression is repeated with 1 or more clock cycle delays between the repetitions, and the evaluation terminates at the last Boolean expression. The timing diagram will illustrate it. Okay. Okay. The second part is that actually this what does it mean by this go to repetition? It is the B not necessarily that consecutive 3 cycles will be B. There may be delays actually in between where B may not be true, but when we get 3 matches of B, then we can proceed. Okay. So what it does is that not B for 0 to any time, not B for, that is B is not as for how much long it can be, but when a B is done, this thing should be repeated 3 times. The timing diagram will illustrate more. Look here, the evaluation attempt starts at clock cycle 3 where A matches first, then in clock cycle 4 B matches, clock cycle 5 B matches, clock cycle 6 it B doesn't matches. Okay, clock cycle 7 also B doesn't matches. So B matches for only 2 times, 1 time remaining for B to match. In clock cycle 8 B matches. In the immediate next clock cycle there must be a C. That is the difference between go to and non-consecutive, which will come afterwards. In the next clock cycle, then it is not matches.
Then the counting of B again starts from.
Yeah, then the property actually fails. Okay. But it may match in the latter simulation cycle. This time the property fails.
But counting of B starts from 0.
Again starts from 0. And which is not in the case of non-consecutive repetition. You see here, we also can specify a delay here where B is not asserted. The timing diagram will illustrate. Look that here C is 0. A started evaluating, A matches at 3, which started evaluation, then B1, 2 times B matches, then B falls. The third time B matches, but again B can drop. When C will be 1, it is 1, fine. But if again B comes, then this sequence not matches because we have specified the 3 times only B match. So the go-to repetition and non-consecutive repetition differs only in this fact, that the last delay can be there in consecutive, non-consecutive repetitions, but go-to repetition will not have such. Go-to. Okay. In the go-to repetitions, the final B that occurs must be followed by that #1 C. The next cycle we must have C1. Otherwise, if the B lowers before C gets up, then the sequence will not be verified, will not get satisfied. Okay. In non-consecutive, we can allow that also. We want 3 times to be B1 any in between in between A and C.
The non-consecutive repetition also is that B must be equal to 3 or maybe greater than.
No. This is equal to 3. If it gets 4, then it's not matched.
It has to wait
three till but the next after the last match of B, it must follow with a C, not with like this, not in the 9th clock cycle. If you look here in the 9th, the B lower, but C when it gets up, it is true, not like that. And there are some okay.
If you want to say that B is more at least 3, if it's more than or equal to 3, then how will you represent that?
More than 3 colon. I said that if you can specify the range like here, like this, x colon y, 3 to 4, 3 to 10.
So in that case, what will be the value of y? That is greater than equal to 3.
Yeah, it must be greater than equal to 3. That's a range. B must be 3 times, 4 times, 5 times, till 10 times. Between those range. Okay. Then the AND operation is that you can also specify this AND binary operations between those sequences. AND operator is used when both operations of the expressions are expected to be succeed, and end time of the operand can be different. That is, this is a 2 times span sequence. This is a 3 times span sequence. So how the timing diagram looks like: A #1 B, this matches here sequence 1 in 4. Look here, A matches at 3. Then next in the next B matches. It also matches here because A matches at 4 also, B matches at 5. So sequence 1 matches in 4 and 5. Once sequence 1 matches, then we try to find when sequence 2 matches. When sequence 2 matches, then the total match happens. It may be vice versa. Sequence 2 may match earlier than sequence, but when the total when 2 of them matches together, then we say that these two the total sequence matches. Similarly, there are intersections where the binary operator intersect is used when both operands or expressions are succeeded. N times of the operand expression must be same. Like here, n times means the time span of both this sequence which you want to intersect must be same. This timing diagram will show how. A #1 to 3 B. That means there must be 1 cycle, 2 cycle, or 3 cycle delay between A and B. So A matches here, B matches here. So here is also a match. Here also B matches, so here is also a match. So the red one signifies the first sequence match. And A #1 B #2 C. That means A matches here, #1 B #2 C, here C matches. So when these both matches here, there is a match of the total expression in the 7th clock tick. This is the intersect operator, which differs from AND. That AND specifies whenever sequence 1 matches, if we get a sequence 2, then finally it matches. There is an OR operation also. But it said that either of the sequence 1 or sequence 2 matches, all the time we will match the total expression. Like this here. The sequence 1 matches in clock cycle 4, we get a total match. The red ones is the sequence 1, and the blue and the green ones are the sequence 2, and the blue is the total. So here that neither sequence 1 or not 2 matches in clock cycle 6. So it's a failure. We can also specify condition of a sequence. Sequences are often occur under the assumption of some conditions. Like look at this expression, that not C throughout this sequence. If not C is C, it does not remain low throughout, then this sequence will never access as a truth. Actually, a logical condition must hold true while processing. Certain values are prohibited while processing a transaction. Like C equal to 1 here is prohibited during transaction. So how the timing diagram looks here? A is 1. First we want to look at this. First we want to look at this sequence. If it is matches while C is 0, then actually it matches. A is 1 in clock cycle 3. In next cycle, A and B should match for 2 consecutive cycles. It is a consecutive repetition. So here A and B matches, here A and B matches. So the final sequence matches here, and throughout the C is low. So it matches here. But here, if you look, that C is 1, though the sequence is matching here, but C is 1. So at the clock cycle 12, the throughout C is not 0, so it doesn't matches. Now an important point, how can we specify the behaviors, like if request 1 is there in the next cycle, we want a grant 1. So this kind of behavior, if then like relationship, if something happens then in the next cycle we want something. This is how we specify implication. Some behavior implies in the next behavior. Allows to monitor sequence based on satisfying some criteria. Evaluations is based on success of the condition. Like look at this property. A data phase completes on the rising edge on which A is asserted and either B or C is deasserted. Data phase complete means at the time data phase signal is 1. We want either A is 1 and $fail B, that means the B either B or C is deasserted. $fail means it's just fell from the logic 1 to logic 0 value. So this is a particular example of implication. So the timing diagram says is that when data phase will be 1, then actually this equation will actual sequence will match. But look here, it is not a sequence, it's a property. We will discuss more on property and what is the difference between it. Just notice it that the implication we must have property, not sequences, because it's not entirely the sequential behavior, it's an if then relationship and some assumption and guarantee relationship. Therefore we must encode it like a property. And the timing diagram it suggests that data phase, when data phase is 1, then the next is evaluated, then it is true. When data phase is 0, there is no question of evaluating it. No, that's implication. That's the system value of construct. I mean, it seems that if data phase is 1, we will validate the next. If data phase is 0, there is no meaning of.
If data phase is 1,
Yeah.
then we will check for this.
This, yes. Yes.
That is, we check if A is 1 and
Yeah.
what is dollar fill? It means from 1 to 0.
1 to 0. The logic fails from 1 to 0.
Or from B, C first from
1 to 0. This is the property.
This was happening in the same clock cycle.
Pardon?
Same clock cycle as data phase becomes 1.
Yeah.
The same clock cycle.
That property must hold in that clock cycle where data phase becomes 1. Okay. So in the master okay. Look here, A is 1 in this clock cycle and then $fail B is yeah.
In the diagram,
Yeah.
show you an example like at Russell's time,
Yeah.
C is not falling down.
No. It may fall from in the previous from previous time step actually. Yes. Once it falls, the $fail is 1.
It means that basically dollar bill C means that at that particular clock
Yeah.
cycle she should be 0.
Yeah.
In the fifth clock cycle, E is also falling from 1 to 0.
In the fifth clock cycle, B is no, B is not falling. B is 1. And it's a OR relationship. How does it matter actually? I mean, it's a OR relationship. If C falls, it's fine. Okay. And in real case, like in master checker, we revisit the master checker case. A master should not reassert its request signal until the current transfer terminates. So look at the property in the bottom that past there is a request and now there is not a request. Past means in the previous clock cycle. And so it implies that request not asserted.
Does that mean falling from 1 to 0 or just equal to 0?
Just not just equal, it fails sometimes earlier, then it's failed. Oh no, it's sometimes earlier. That is in intermediate some time steps we have captured those timing diagrams. Okay. Sometimes it failed, it's 0. Yeah, I want to introduce some of the constructs. You can. At that point of time, C is 0. Yeah. So now the property, as we have mentioned, that the property defines a behavior of the systems. So it may be an implication like in the first P1 and P2 property. It may be a sequence. So all sequences are properties, but not all properties are sequences. So what does there is a new construct is introduced here is this in the property P2. Actually, it's a non-blocking implication. The previous one in property P1 you see here, it's a blocking implication. What does it mean is that the sequence one is evaluated suppose in time cycle 3, the property one will start to evaluate from time cycle 4. That is a blocking evaluation. The time cycle ends in the next time cycle, and this is non-blocking. Sequence 2 evaluated at time cycle 3, property 2 will start evaluating from time cycle 3. So here you see that how these two are equivalent. This sequence 2 non-blocking implication, property 2 means sequence 2 next clock cycle true, assuming blocking implication. So a property can be used as an assumption, as a checker, and a coverage specification. We will see this. First, let us briefly discuss about the classifications of it. There are concurrent assertions which describe the behavior that spans over time. Evaluation model is based upon clock, and the values of the variables are sampled in the specified clock ages, as we have mentioned. In case of at the rate of pos age clock, you also can mention at the rate of neg age clock. I mean, the pos age signifies the positive age of clock. And you can specify a property like this. Actually, the grammar is like this: assert, it may be assume, it may be cover, property P1, then there is an action block. I mean, if this property succeed, you may want to display something, you may want to do something. So this is the action block will signify, or else there is also something you must do. And there is an immediate assertion. Immediate assertion is just like your C assert statement. It's a Boolean expression based inserted within the test bench code. You can insert it, and based upon that you can evaluate and then specify your action. So immediate assertions follow the simulation event semantics from their execution, like the test bench executes over the duty. Immediate assertions are executed like a statement in a procedural code. So like here is an example: assert a dollar display. Dollar display construct actually displays when the design simulates displays in the monitor that this passed and failed, like printf in C. And some of the failure of the assertions have such severities, like dollar, when dollar fatal, this kind of thing will terminate the simulation. Dollar error is a runtime error, and dollar warning, you can also specify here, is a runtime warning. And dollar info failure carries no specific severity. In the lab, when we will actually write this and simulate it, you will find these things when it comes, where it comes into picture. So property as an assumption. By assumption, I want to means that this thing, there are some assumptions in the design, like the design should behave under these constraints. These are the constraints. Allows a property to be considered as an assumption for formal analysis as well as dynamic simulation. As I mentioned earlier, this in case of formal analysis, this is an hypothesis where you formally analyze a design exhaustively. These assumptions will ease you to verify the design with less exhaustively, because some assumptions will carry out there. For simulation, the assumed properties must be checked. Like let us take an example that request can be raised at any time and must stay asserted until acknowledgement is asserted. In the next clock cycle, both request and acknowledgement must be deasserted. So request is, when request is 1, request can be raised at any time, like at the rate of passage clock, the first property, request is 1. Then request may be asserted until the end of simulation. It must be asserted until acknowledgement. So it can be asserted any time, and then #0 means without any delay. When acknowledgement comes, it doesn't. And in the next clock cycle, both request and acknowledgement must be deasserted. So which is what is there is this property is capturing that when acknowledgement is there, request is not there. This is the first one, is it must be stay asserted until acknowledgement is asserted. When acknowledgement is 1, it must flow. And the second property in the next clock cycle is captured in by this PA1 and PA2, that not request implies not acknowledgement. If I don't request, what is the need of an acknowledgement, like this? And if acknowledgement will stay only for 1 clock cycle, like that, in the next clock cycle, both request and acknowledgement must be deasserted. So the first two is an assumption property, this PR1 and PR2. We write like this: assume property, and the next two is an assert property. By this assumption, we want to verify the next two property. So assertion actually the assert statement is used to enforce the property as a checker. We want to check this behavior. It may be under some assumption, it may not be under some assumption. It is specified by let us see this example. It is how it is specified. You can specify a sequence like this, and you can embed that sequence in a property. You can say that assert property, or you can also specify within the S1 directly here, and you can say assert property. So when the test bench will drive inputs and collect the responses from the duty, what we will try to do is that it will send some value and get some value back, and try to validate this sequence to assert property. If it finds no values that can satisfy till the end of the simulation, it will say that this cannot be validated, this cannot be checked. So this is how it can be used as a checker. Like this, the master should not, the same example here also, we just write here assert. I want to tell that this assert is the construct, and this assert one is a level. You can, it just acts as a level you have used in C actually. I mean, it's nothing to bother about this. This assert, how you can write. And here is the important question, that is coverage. And coverage by I mean is that we want to monitor that how much behavior we have specified, how much it is ticked, or how much it is verified. If we simply write this cover, what it will do is that it will tell you several things. It will tell how many times this property is attempted. By attempted, I mean how many times the evaluation attempt starts. Like when B is 1, it started, but in the next cycle may not be C is 1, so it fails. How many times it is failed, it will report. How many times we can cover it, that is totally true. How many times it cannot be covered, like these things. Again, this is to see whether the cover is used like this. The cover property in the same example, the cover property, cover construct is used like this. And the coverage results can be divided into two parts, like coverage for properties and coverage for sequences. The identifier of particular attempt is called attempt ID, and the clock tick of the occurrence of the match is called step. And these two things are specified in the coverage result. You will get a coverage result when you simulate the design with this cover property construct. So the results for coverage statement for a property will contain, as I said, the number of times it is attempted, the number of times it is succeeded, number of times it is failed, number of times success vacuously. There is a new term introduced, vacuously. In the implication, we have seen that request, like let us take a small example. Request in this cycle eventually will be, in the next cycle we want to grant. Request implies #1 grant. This is the property. So if request 1 comes, in the next cycle grant 1 comes, the property is true. If in the next cycle grant 1 doesn't come, the property is false. But what if the request doesn't come? Then there is no meaning of verifying that property at all, because we said that if request comes, we want a grant. If no request comes, we don't want anything to verify. So these cases are called vacuous cases, where the antecedent of the implication fails, no matter what the consequent value is, it is true. So this is vacuous. It also says that how many times it vacuously matches. So by reporting this, you want to, sometimes some happens is that some property is not triggered at all. So it is true because it is vacuously true. By reporting this, what it says that there is an error in the test bench, or you have not driven actually the request. So the test bench engineer will again have to modify and remodel his test bench so that this assertion gets checked non-vacuously. Each attempt with an attempt ID and time. This is some informations carried with this coverage reports. A success and failure with attempt ID. Vacuity rules are applied by implication operator. Otherwise, it is not applied. And the property for coverage in sequence statements is number of times is attempted match. As sequence statement doesn't contain any implication, as I have said, so there is no vacuous case here. And each attempt with an attempt ID and time, each match which a clock step attempt ID and time. So here we are. We have a coverage monitor here. The environment is a test bench. We drive inputs, collect responses. The assertions is in between them. We try to verify a match failed report goes to the coverage monitor. And finally, we get that these are the properties we need to verify, and these we have verified. So we get here a layered modeling. First, we express a sequence, then the sequence is used in a property to represent a particular behavior, a context. And then in the top module, we assert or cover or assume that property. And this layer modeling helps us for the debuggability and also the modeling of the test bench and design to verify. Now the clock domain, I have introduced like at the rate of passage clock. I mean, that means the sequence of the property gets validated with respect to a design clock. So it also supports multiple clocks actually. I mean, concatenation of two sequences for each sequence can have a different clock like this. Like at the rate of passage clock, a design must have 2 or 3 clocks. Several clocks there may be in design. If you want to validate a property which spans over 2 or 3 clocks, what you will do? Like this. At the rate of passage clock 0, signal 0 must be 1. And in the next passage clock, signal 1 must be 1. In this kind of the antecedent of the implication is on one clock, and the consequent in another clock. It is also possible. But what is not possible is that there is some rules in clock resolution. Multi-clocked assertions are not allowed to be defined within a clock domain. Like if you define at the rate of passage clock 1, within that at the rate of passage clock 2, I mean if you define in sequence to here at the rate of passage clock 3. This is not possible because you cannot drive the other 2 clocks within a clock. So within a clock, in a procedural clock where a clock is inferred, it is not allowed. And for a multi-clock in assertions, the clocks are explicitly specified. I mean, these are design clocks. We are using those design clocks. No default clock or inferred clock is used. So here are some of the important details of system Verilog assertions. Like what happened if we want to verify such a property that pipeline is out of order or not? I mean, you have to store that if x some input value you want to store in some x variable, and suppose when it executes the pipeline and goes out, you want to check that it is incremented or not. So you must need some variables. Would you use some static variables? It will waste memory. So you have to have such a way that a variable must be you must be actually allocated to the memory when the assertion checking starts, and it must be deallocated from the memory when assertion checking ends. This kind of thing. These are called local variables. It supports actually system Verilog. It supports this, and it supports a dynamic creation of variable, as I have mentioned. Just during those assertion checking, it creates and destroys. Used within particular transaction checks like particular behavior over the sequences, and can overlap with other transaction sets, supports out of order modeling. Like in pipeline, you will find in the next example. Life starts at the start of evaluation attempt for the sequence, when the sequence or assertion of property starts checking, and life ends when the end of the sequence is reached. Look at this example. This int x, in the property we define this is a local variable. What we do is the validine, suppose it's a select line of the pipeline. If it is true, then x goes into piping. And next, if it's a 5-stage pipeline, suppose it works in 5 cycles. In the after next 5 cycles, what we want is pipe out is incremented value of x. So x is assigned to pipeline when validation is true. E is true if 5 cycles later x is equal to x plus 1. This is how the local variable is used. Actually, this variable creation or allocation starts when the property checking starts, and it ends when it actually ends. Here is a running total example actually for the whole system Verilog assertions. As I have mentioned earlier, a little bit of master interface. The interface is like this: master device request for transfer. It holds the transfer information. There is a specification, so we will use it in the lab. We will implement this some of the properties in the lab and verify, right? So I am giving some hint here. It holds the transfer information till the address cycle acknowledges it. It deasserts its request signal once the address cycle acknowledges. There are some specifications specified. And what are the properties like here is that it follows this behavior. Like master request for a read transfer, M3 request. Suppose the master 3 request for read transfer here. Address cycle is acknowledged at address cycle acknowledged at cycle 4. That means LB final request is the address acknowledgement it done in cycle 4 here. Data cycle acknowledges cycle 5, that is cache access logic done, data cycle come, and transfers therefore successfully completes at 5. Here the address cycle acknowledgement done, here data cycle acknowledgement is done. So transfer completes here, we get the data here. So how to specify such of this interface? How we can specify some specific some properties here. Master device request for transfer. It holds the transfer information till the address cycle is acknowledged. This is an important behavior. It has to hold the transfer information. Otherwise, if the transfer information it puts it down, then we will not get the data. Suppose the other device is not ready at all. So for what will be the $rose mn request? Once it asserts the request, and this is the address cycle is till not acknowledgement, till the you will find how many till the end of the simulation we will look for it. Once it is true, then in the next cycle we can acknowledge it like this. LB final request is the acknowledgement coming from here. We see that this is the acknowledgement. And similarly, the master should not deassert its request line once address cycle for the ongoing transfer terminates. So this actually this implies not mn request. It cannot deassert its request line until the transaction is going on. Now, an important topic is I have said that these are the temporal nature of a design is captured through assertion. By temporal, I mean time. It spans over the time. So there must be some logic actually. Actually, this formally there is some logic called linear temporal logic, which specifies this design behavior over this time span. I will express this what it means. Actually, GP means a design must go through some cycles, some steps. These are the steps a design goes. These are the states in the design. These are the states in the design that design should go from in each cycle. This GP actually means that throughout the execution, whichever state design follows, in every state the property P is true. That is marked in red, satisfying P. Look, from the start state, the whole property is true. This kind of behavior is needed. Future P, that means that eventually I will get P true. It may not be may not be next to next, but eventually in some cycle I may get P true. This is expressed by FP. These are actually used. You will find it more in the formal property verification part. These are actually used in formal property for those theorem proving and those cases. Next P, that means from the start state, in the next state the P is true. And P until Q, this is a very important operator, that P this happens until a Q occur. This is the blue, the green specifies the state satisfying Q. So why I mentioned this is that there is an equivalence between this LTL with SVA. Here is it, like next P we have modeled it by hash 1P. then the next cycle P is true. By future P, future means till the end of the simulation there must be a P, that is 0 colon dollar P. By global P, I want to mean that P will be from 1 to dollar any time throughout the execution, throughout all the steps. By P until Q is that first cycle there must be a Q, it's true. P until Q means that it will finish this sequence with a Q, so Q must be occur, then it is true. Or P any time followed by a Q. If the first time Q occurs, it's true. So there are quite certain similarities between these two. That's why I expressed this. So we have covered those specifications which are based on temporal properties. Supports the specifications of regular expressions this time specified over the time. It supports a layered modeling for the hierarchical design and test bench. It supports local variable. It supports assume guarantee style of specification. It will this assume guarantee style of specification is much more needed if you have a large block and if you want to verify an intermediate block within the large design. Then you have to assume some signals values, because you cannot only that block you cannot verify without assuming the values from the previous blocks for the coming. Use assume guarantee specification. It will more be covered in the formal verification lecture. It supports assertion coverage. It's a very important issue. From this, the designer actually know that their design is incomplete or complete. It supports multiple clock domains. So we conclude here that assertion provides an unambiguous formal specification. As you see that it can be specified formally using system value, so it's a formal specification. Assertion catches design bugs very early in the design cycle, because you write a design, you write a test bench, simulate just assertion monitor monitors and says to the test bench writer or the design writer that you have not verified, that you have not properly implemented a design, or you are not properly driven the signals to the design to verify it. During simulation, assertion attempts to provide functional coverage of the specification, measure the uncovered space. Actually, it's a coverage space. 40 properties want 40 functionalities we want to verify, 30 behaviors among them are verified, like that. Can also guide the simulation. By guiding, I mean there is something the properties or the assertions that are not verified. If that request implies grant, that request is not asserted. It tells the test bench engineer that you must assert the request here in this context. So test bench it guides the simulation through that path. It supports formal and semi-formal analysis in this way. So these are the few references. The first one, the chapter 17, you can find the assertion. In the first one is a very important manual from Accelera, and it's a slide from Daniel Brauch, and this is a good report. It is available. You can find the assertion specification and its usage. It's a synopsis report. These are the. So you can mail me if you have any query, and you can ask here also.